All right, so for those of you in class, I've just handed that homework back. Everybody get that? There were a couple of you that came in late, so James, Jonathan, Joey, Morgan, Brandon. Okay, so when I was going over this stuff last night, I was looking at that, and some of you are getting the right answers, but I was a bit concerned about your method, which, is kind of an important part of getting the right answer, obviously. So if I'm going to do this 272, what I'm going to do is I'm going to look at that thing. I'm going to see a pin joint at A. Okay, when I see that pin joint at A, what I'm going to do next is go, okay, I'm going to take moments about that because that will allow me to solve for the cable force at C. And then once I do that, I'm going to say, okay, I need X and Y dimensions from A to C. So I'm going to take that angled part of the bracket there from B to C, and I'm going to do a bit of trigonometry on that. Sine and cosine of 30 times 2.6, and I'm going to get those red dimensions, the 1.3 and the 2.25. Okay? Now, I'm not going to trust myself to remember that stuff. I'm going to draw it right there is what I'm going to do. Okay? So I'm going to put that dimension on there and label it. Then I'm going to take moments about A. Okay, so I've got the forces at the pin joint, I got the force in the cable, and I've got those dimensions. Notice everything is right there on the sketch. I'm going to look at the sketch, and I'm going to do a moment about A. So I'm going to take cosine 58 times 7,000. That's going to get me the component of that force going to the left. So that's going to get me that right there. And I'm going to multiply that. That being an X force, I'll multiply it by the Y dimension. 1.2, it's clockwise, so it's negative. Then I'm going to take cosine of that angle, 50 degrees, times TCD. And that's going to have a 1.2 plus 1.3 equals 2.5 meter moment arm. That's going to go counterclockwise, so it's positive. And then sine 50 TCD times the X dimension, 2.25. That'll also be positive, okay? So by drawing that sketch, putting the dimensions on it, labeling the forces, the moment equation is not that challenging. I can just look at it and do it. That's kind of what I'm trying to get across to everybody here. I get that strategy figured out, then I create a nice user-friendly sketch, X and Y dimensions, forces right on there, then bang, I can just knock out the moment, okay? And I've got all the signs in there in the proper direction, and I know the sum of them is 0. So we got any questions on that? Okay, and that'll get me TCD 2296 as assumed up and to the right. Once I've got that, I can go sum of Fy and sum of Fx, set them equal to 0. So I got Rex to the right. Cosine 58 times 7,000 goes to the left. And then cosine 50, 2296 goes to the right. So that will get me the sum of all the forces in the X direction. So I got that, and then I got Rex, solve for Rex, 2233, and then I'll get the Y components also. So Ray minus sine 58, 7,000 plus sine 50, 2296. And that's 4177. All right, are we good on that? Okay. So don't shortcut things. Don't skip steps because that leads to errors sometimes, okay? Okay, this one here, whatever the heck this was, 276 or something. Yeah, question.
Did you go full screen sometime later?
Yeah, I can try. That gets me into trouble sometimes. But yeah, let's see what I can do. Slideshow from current slide. Sometimes when, okay, yeah, that's better and that's working, I guess, for everybody. Okay, yeah, is that good? That's about as big as I can go. All right. So what we got there, we've got, this one's a little bit more complicated, isn't it? So again, I just label every dang thing on that sketch because then I can see it. Okay, when I start trying to juggle things in my mind while I'm making a moment equation, I'm just not smart enough to do that. I make errors, okay? So I get a nice clean sketch. The sketch, another word for that is a free body diagram, right? Now it's not really looking like a pin joint, but that's a pin joint right there, okay? Oh, this is hopeless. Let's try that. Maybe this will work. There we go. I'm going to take moments about there. I got two unknowns there, plus I have the unknown force in the linkage from C up to that pin, okay? Now, I know the force in the linkage follows the linkage. I got 131 degrees, so if I take 180 minus that, I get 49 up left for RC. I've got a distributed load. I take 4,000 newtons per meter times the 0.9 meters that it acts over, and I get 3,600 newtons. That's right there. I've got cosine 58 times 0.28 and sine 58 times 0.28. That gets me the dimensions on this little angled armature right in there. Okay? So I put those again right on the sketch. So I just go ahead and put those dimensions right there and right there. Then I go ahead and add everything up so I get the dimensions from A to whatever I'm looking for. I've got this 3,600 Newton force acting at the center of this rectangular weight. So I take the 0.9 and the 0.45 and I get 1.35. I take the 0.9 plus the 0.148 and I get 1.048. That's from A horizontally over to that point C. Okay. So I had to take that angled linkage BC, or it's not a linkage, it's just an armature, and break it up into X and Y components. Okay. All right, so see now I got that picture, it's good to go, then I can just write up the moment equation just one at a time. I've got that couple there applied by the motor, it's clockwise, so it's negative. I've got the weight times the offset distance, so the Y force, X offset distance. I've got sine 49 times whatever RC is times 1.048. Sine 49 RC gets me the Y component. And then I've got cosine 49 times whatever RC is. That's the X component, you know, right there. The Y component was up here. The X is there. That X will be times 0.2375. Both of those are counterclockwise, so they both get positive signs. I can find RC. It's 6821. Okay. Once I got that, I can go sum of fx, REX to the right, cosine 49 times the 6821 to the left, REX is 4475. Sum at Fy is REY plus sine 49, 6821 minus 3600. REY comes out to be a negative number. I assumed it up. It's not up, it's down. Okay. You okay with that? Yeah, question?
How did you get the 1.048?
Okay, the 1.048 dimension comes from this dimension right here, which is cosine 58 times that little armature sticking out. That's 0.148. Okay,
Right.
that's the X.
It doesn't look like the lineup right there.
Oh, yeah, it might be, yeah, that's a bit off. Yeah, that'd be coming in just a bit, wouldn't it? Yeah, then I add it to the 0.9 down here. That's where the 1.048 comes from. Okay. Other questions on that? So that's the deal on that stuff, okay? And, part of this class is teaching you how to do statics, but the other part of it is starting to get you to think, as engineers do when they solve problems. The more you can be a human spreadsheet when you're working through this stuff, the better off you are, because you're more systematic, less errors. When you make errors, you can track them through, fix them, okay? That's a good skill to have, okay? Okay, so I just want to go through that a bit. Well, let's see. All right, so that's that one, okay? Discard, there we go. Okay, let's look at the next thing down the line here, and what that is frames and machines, okay? So these are kind of like trusses, but they're just a bit trickier, okay? So we want to get those figured out. So let's have a look. So what we have with frames and machines is they're put together of separate pieces, like trusses are, but they're not all two-force members. So they're, as I say, they're just a little bit more involved. And maybe we'll take this option. Okay, there we go. So there's a bunch of frames and machines. Basically, frames don't move, and they support a static load, like a bike rack on the back of a car is a frame. Machines move, exert a force, and move a load. So a pair of vice grips would be a machine, an oil derrick, backhoe. Those are machines, okay? So there are some similarities between these and trusses, but some differences too. So on page 560, we've got some stuff about frames and machines. So you kind of think of in terms of trusses, but also think in terms of viewing these things apart, pulling these things apart. What we're going to have on some of these is we're going to have some of the members are 3-force members, okay? Not just 2-force or 4-force members. So you can't just assume that the force acts from one pin to the other. That's often not a good assumption for the members that make up frames and machines. All right, so I have a couple examples here, just little notes about how we analyze this. If I just have a simple little thing here, I've got this block or bar attached to the wall, welded there, or somehow a fixed support at C, and then I've got a pin joint and a linkage, and I'm pulling at A. Let's kind of track that 30 Newton force through and see what it does. All right, So the first thing I'd be looking at here would be linkage, AB. I'm pulling on it at A to the left with 30 newtons. So to counteract that and hold the thing in equilibrium, there'd have to be a pull to the right of 30 newtons at B. So that's actually a two-force member there, that one is, and it's in tension, okay? It's being pulled apart. Now, the something that pulls B to the right with 30 newtons is the pin that is inserted here, this little pin joint right there, that pin itself. So if I look at the pin, what AB is going to do on it is pull on it also. So it's going to basically compress that pin as it does that. So there's going to be a 30 Newton force exerted by the linkage on the pin itself. Now the pin's in equilibrium. So what's going to happen there is I'm going to get a, let's see here. So on that pin, BC is going to have to come back the other direction on the pin to hold it in equilibrium. So AB is going to the left on the pin, so BC is going to pull on the right, to the right. Now what that means is we turn the force around again for what the pin does to BC. It pulls it to the left. Okay? And then there's a reaction at C going to the left with 30 to hold it in equilibrium. So a couple points here. First thing is that you kind of switch the forces as you work through these things. Okay? So if the pin pulls on AB to the right, AB pulls on the pin to the left. Okay? They have an equal and opposite action-reaction kind of relationship there. The other thing is you can just omit the pin from the whole analysis and just look at AB and notice that that 30 Newton force is to the right. So at B on the BC, the 30 Newton force is to the left. So often as we analyze these things, we ignore the pins and just kind of work from piece to piece or member to member. Okay. So y'all okay with that? Okay. All right, now kind of on that vein, we get into pulleys here sometimes, okay? So let's say we got a bit of a pulley there. We're going to hang that 200 Newton weight from it. And on the right side, that cable is attached down there at a 60-degree angle. Well, what that means is if we cut a free body diagram of the pulley, we could draw up a picture of that. And that's going to look something like this. We're going to have that 200 Newton force down on the left side from the cable. And over on the right, it'll be down at 60 degrees. Okay. Now to hold the pulley in equilibrium, notice that this is essentially these moments would balance out, so the pulley itself wouldn't spin. In each case, we'll have 200 newtons times whatever the radius of the pulley is. So what we're going to have here are force reactions of the pin on the pulley opposite to those tension forces being exerted by that cable. So we're going to have an upward pin force to counteract the one on the left, and an up left at 60 degrees pin force to counteract the one on the right. Okay. And then what we could then do is look at how the pin pushes on this support, and it'll be the opposite of what the pin is doing to the pulley. Okay. So we'll have a downward force and a down right force at 60 degrees that the pin pushes on the support with. Okay. So we're doing the same sort of analysis here as we work our way across. We're changing the directions of the forces as we work our way through, and we get down to this. So when you have a pulley, what you normally do is go right to the pin right there and apply the cable forces directly to the pin, and that generates your free body diagram of the support. That allows you to ignore these little dimensions here that you would have to consider when you're looking at moments. And you'd have to look at dimensioning to these places where the cables are applied to the pulley. You can just ignore all that and just put the cable forces right at the pin by doing this kind of step-by-step analysis, which is the simpler way to do it, because when you do it that way, you'll have the dimensions you need that go right to this pin, as opposed to having to figure out those pulley dimensions every time. Okay.
How many forces are there? Is that 4 or 2?
On
Well, the whole thing, the whole free body.
Well, you kind of have to define what you're drawing a free body of to determine how many forces there are. I mean,
so there's one of the pulley and then one of the support. Okay.
That's a full free body diagram of the pulley, and there's 4.
Okay.
Now here on the support, there's 2 at that pin. Now I haven't really shown anything down there though. Okay. All right. Other questions on that? Okay. Okay, the last thing on these is you got to be careful. You can't just do your truss stuff to these frames and machines. For instance, ACG is not a 2-force member. It's probably a 3-force member. What that means is you cannot just find this force, this reaction at the roller, and then have a force going through ACG that counteracts it, and use some trigonometry and solve for that ACG force. The reason is that ACG is not a 2-force member, it's a 3-force member. And if it's a 3-force member, you can't assume that the force follows the line of the member. You cannot make that assumption, okay? So I can't assume that RAY is FACG times sine 30. It's not going to work that way. It's more complicated than that, yes?
Why would it be a 3-force?
It's a 3-force because there's 3 pins. There's one at A, one at C, one at G, each one of which can introduce a force.
It's because the force is coming across instead of down the line.
Across.
Like where the force is positioned in the problem.
Mm-hmm.
It's coming out like outside rather than down the line.
Well, I see. So it's not even a function entirely of that. If you apply that force, even if you apply the force up here, I think you're going to get some sort of counteraction from CB. So it just has, the main reason I would say that ACG is a 3-force member is there's 3 points of attachment. And I have no reason to think that any of those are 0 necessarily. Okay, so there's 3 forces. Okay. All right, so that's just some basic concepts we use when we solve for these things. Now, when you start analyzing these things, you're going to pull them into pieces, and you're also going to look for 2-force members, because if you can identify those, you can simplify your analysis. So here we got a bucket here that's loading up a dump truck. See any 2-force members on that thing?
It looks like those hydraulic things are.
Yeah, I think those hydraulics are, right. So the hydraulics are 2-force members on this, okay? So, you want to get in the habit of finding these, because if you can find them, the analysis is a lot easier. So these hydraulic cylinders are 2-force members, okay? So let's have a look at this problem here. I think you all got that. It's on the next page, eh? 570. Okay, thanks. So it's 570. So we're going to hang a 3,000 Newton force at C, or a weight, and we're going to want to find the forces in the joints, A, B, C, D, E, and F. So, first thing I want to look for is find any two force members that make up that frame. Okay, that'd be called a frame now. And notice, for instance, that ABC is a 3-force member, not a 2-force member. So it's not like a truss anymore. What's that?
Looks like BD is.
Yeah, I think that's the one, okay? So when you look at BD, what you're going to see is a linkage, basically, with 2 pin joints and no forces anywhere in between B or D. So BD is a 2-force member. Now, that's important because it will simplify your analysis a great deal when you identify that. So what that tells me then is the force at B is horizontal. Okay, it's a 2-force member, so the force follows the lines of the pins. If it were not, I couldn't assume that. See? I wouldn't know the direction of the force at B, but that is a 2-force member, so I'll have a horizontal force at B. That allows me to make that assumption. Okay. Okay, so I represent 2-force members as just forces on my free body diagram. I don't even show them as linkages or whatever the heck they are. I just show them as forces because they're simple and I can just model them that way very easily. Okay, simplifies what I'm trying to do. All right, so let's see. Now, what you do with these is similar to trusses. You break them up into pieces. Okay, so I'm going to start with that left-hand armature. I'm looking at the one on the right, the EADH, I think, or F, EADF. There's just so many forces on that thing. I don't want to mess with that yet, okay? So what I'm going to do, I'm going to look at ABC, and I'm going to say, oh, okay, there's only 3 forces going on with that thing. I can solve that. So I'll start with that angled linkage or angled member on the left. And what I'll do with that, of course, I'll make a free body diagram out of it like I do. And I'm going to assume directions for AX and AY. Now, what am I assuming about BD? Am I assuming tension or compression for that one?
Compression.
Yeah, I'm assuming compression because that's pushing is what it's doing. Is that a reasonable assumption there?
Yeah.
I think it is, yeah, because I got that weight going down, and what that weight's going to do is try and swing that member like so, and BD's going to push back, okay, and that's going to hold the thing in equilibrium. That looks like a reasonable assumption to me. Okay, all right. Okay, all right, and then I'll just throw my statics at it. See, I'm going to start with ABC. So this time I'm going to drop a free body diagram. I'm also going to label what I'm working on, and it's ABC. And it's just a regular old statics problem. I've got 2 forces up at A, so I'll take moments about A. So I'll have the 3,000 newtons times 0.75 meters. That's coming around counterclockwise, so that'll be positive. And then I've got minus, because it's clockwise, BD. That's an X force, so I'll use a Y moment arm of 48 centimeters with that. And that'll be clockwise. And then I'll work my way on through that, and I'll get FBD, and that's 4,688 newtons. Okay. So the idea here with these frames and machines is you break things up into simpler pieces that you can deal with and solve out the simpler pieces, not the thing as a whole, but you kind of break it up into pieces. A drafter would call that an exploded view. And then from there you can go ahead and solve for the forces acting on the pieces. And then what we're going to do next is kind of work the forces through the overall object. See, notice I've got some common points. I've got A is common to both pieces, the left and the right, and that force BD is also. So I can find things on A, B, C, I think it is, and use that information and take it over to that long vertical piece. Okay, that's the idea here. Okay. All right, now once I got that, I think I'll just, I've got the BD. I've only got two unknowns left, AX and AY. So I'll just go ahead and go sum of FX and sum of FY and get those figured out. Okay. So 3,000 newtons up here, just basic equilibrium, and 4,688 newtons here. Okay. And that's enough to hold that thing in equilibrium. Okay. Now I got the forces now at A and B, and I got the 3,000 down at the bottom of that thing. Now I'm going to take those forces and bring them over to the other side now, okay? Now the one important thing here, or well, I guess there's always more than one important thing, but the one thing I like to emphasize here is you got to turn them around. When you go from ABC over to that EA, D, F, you got to turn the forces around. Okay, so on this side, I've got A is right and up. So on this side, A is going to be down and left. And that's really important on these things. That's one of the big things to remember. Turn the forces around when you go from one member to the other. And you've already been doing a bit of that with trusses, right? So if that linkage BD is pushing and is in compression, it's pushing on that angled linkage on the left. It's also pushing on the straight linkage to the, or the straight member, I should say, to the right. So it's to the right over here on the right and to the left on the left. Okay. You all good with that? So turn the forces around as you go from one member to the next when they're connected. That's the one big important part of this. So you create an exploded view. You kind of look and see, well, where can I start? You know, you got to start at a known force usually, and start with something where you can work statics equations to get started. Then you turn forces around as you go from one to the other. Okay. Okay, so I'll bring those over there, okay? And now I count them. I got EY, EX, and FH. So now I got three unknowns, see, once again. So I've eliminated a bunch of those unknowns by using the forces I found on ABC. So I can pull that on over to the right-hand member now. And we're just think for 1 second, because this might be coming up on Monday. Where are you going to start? What's your equation to start with to analyze that vertical thing? Everybody just think on their own for just a second. What are we going to do? And the winner is a moment about probably E. Yeah, that'd be the place, okay? Because you're going to eliminate two unknowns. Do it right there. You'll solve for the one on the bottom. FH, okay? That's what I do. So I get the dimensions I need in there, and I take a moment about E, 4688 times 0.2, negative because it's clockwise, that's this one. And then I've got 4688 going the other direction, that's 0.68. It's 0.68, that's positive. And then I got minus 0.92 times FFH, that one. So I can go ahead and solve FFH, it's 2446. That gets me one of them. And then I got two unknowns, EY and EX. Okay. And from there, it's just sum of fx and sum of fy, and then you got it, okay? Sum of fx, we got fex, the unknown, minus 4688 at ax, and then plus 4688 at bd, and then minus 2446 at fh. So fex is 2446 to the left, and then sum of fy, I got fey up, 3000 down. So fey is 3000 up. So notice I did this thing without doing reactions at all. I didn't treat the thing as one whole object and do reactions. A lot of times that's a waste of time if you've got kind of different pieces that are interacting together. So my first inclination on a lot of these is just to break them into pieces, start to work through them. Okay. So there's a frame and machine example and shows how you would work through that and use these kind of relationships here. This idea of turning the forces around. You want to identify two force members when you start. You break them up into pieces and work through them. That's the general approach on these. Okay. And frames you can use these for. This is a frame. It's just supporting a static load. Machines move in some capacity. They exert a force, or they can support a load too. Okay. Good with all that? Let me skip that one. I don't think we got time for that one. We got time for this one though. This one's pretty quick. So this ought to be 2 pages ahead. This is a machine here. And machines often make use of mechanical advantage, okay, where you're trying to amplify a force. So for instance, with a car jack, you can lift a car with your own muscle power, right, by changing how that force is applied. Now, what's the price you pay for amplifying a force? Distance, yeah. Because to lift that car, you've got to move your muscles 100 times as far as the car actually goes up, right? So that's kind of how that works, okay? So if we want to find the clamping force of this thing at G, we got some sort of plier or cutter here. We're applying 90 newtons at A and B. We break it up into pieces. There's 3 main pieces there. And I'm going to use the 2 on the bottom because I think if I use that top one, I'm going to have too many unknowns to really work with that very effectively. So I'm going to use the 2 pieces on the bottom. Okay. Those 2. So there's my free body diagrams I'm going to work with. Okay, do you see any 2 force members on this one? Yeah, CD. So identify those. You want to find those and get them identified. Okay, so then we'll turn that into a free body diagram. Okay. So there's FCD, and then I'm going to have EX and EY. All right. Now, the thing I want to emphasize on this one is all I want to do on this is find the clamping force. So what I'm going to do, I'm going to take a moment about E and find that 2 force, which is 3FCD. Okay, that's 240. So notice by just having that little handle there, I've amplified the 90 newtons up to 240 newtons. Now, one thing about this is, so what I'm doing there, I'm taking moments about E. I've got FCD times 3, and then 3 and 5 make 8, and then I'll have 90 clockwise moments, so that'll be minus 90 times 8. So FCD is 240 now. So that's going to be this one, 240, so it'll also be this one now. Now, all I want to do is find the clamping force, so I'm not even going to bother solving for E. I don't care. It can be whatever the heck it is, it doesn't make any difference. I want to find the clamping force. So you can skip over some of these things if you want. If all you want to do is find this, you can skip the force at E, because you got the 240 now at CD. And then we've got the unknown forces at F, and then one unknown at G. So it looks to me an awful lot like I can just take moments about F, right? And get right to GY, which is the clamping force. So I'll just do that, okay? So I'll work with DFG, I'll take moments about F. Okay, this is 240, I just found that out. So 240 times 9 is clockwise, that's a negative, plus 3 GY, because 3 centimeters there. GY is 720. Okay. You okay with that? So that one, you can knock through that one pretty quick. You know, the reason being, all you're looking for is the clamping force. So, you know, you don't need the other stuff. All right, that's a little bit on frames and machines. We'll finish this up tomorrow, I think, and then we'll also review a bit for the test. So let's have you work on a couple of those, 321 and 323. And see if you get those in 15, is that the 22nd? Now remember, you know, I'll record the lecture on Wednesday like I do, and you know, if you're not going to be here, you can submit stuff on Moodle. We will have class though, for sure, on Wednesday. All right.
This stuff isn't on this test, right?
Correct. This is not on the midterm. Correct.